Our first speaker today is David Ratchkov, and he hails from Thrace Systems. He's CEO and founder of this company, which is on a mission to reduce power dissipation in semiconductor devices. Very worthy cause. And he's doing it by developing better tools, modeling, analysis, and simulation environment. David started his career in 1999 at LSI Logic and has spent most of his time working in power-related tools and methodologies. He has an MS in Mathematics and Computer Science from University of Plovdiv, Bulgaria. David?
Dave, thank you very much for the introduction. Good morning, everyone. Today I wanted to discuss system power modeling for the purposes of test, how we do that. As Dave mentioned, I'm David Ratchkov, founder and CEO of Thrace Systems, and I have most of my professional life has been focused on power modeling and tools. I have great personal interest in that. What brings me here today is our product line, which is a set of tools which we call the PowerMeter platform. It's comprehensive and collaborative platform that enables folks to perform power analysis and simulations and see their results. A couple of notable features in that system are our support for IEEE 2416 system power modeling standard. I will have a special section on that to explain how we take advantage of the standard for better modeling of power and specifically for the needs of test, which are typically beyond the normal ranges. And our last product is the design dashboard engine. With that, I wanted to take a quick overview of what's in my slides. I wanted to first start with mentioning what the objectives of thermal and power simulations are. Why do we do that? Define certain aspects of how we do things and what we consider to be system and scenario and use case. Take a brief look at what the system power models look like and how we use them, and describe flows which we have implemented them and how that worked out. And most importantly, I'm going to share a few results of system power models in action. These came out as a result of CDX workgroup modeling exercises that we did. And these would be a very good vehicle to demonstrate some of the important features of system power modeling and how easy it is to model power at a much higher level. And last we can open for question and answers. We want to perform power and thermal analysis for several reasons, and I'm sure that you're all on the same page here, but I wanted to describe this one more time to make sure we understand it correctly. First of all, we want to look at thermals to resolve any thermal concerns. That's a very broad topic, and we definitely want to start with that as early as possible. We don't want to wait till the last moment to be considering what the thermals are. That has implications for the design of the system, for the and for the chip design itself. And also to do that, we need to know power from different aspects. We need to know what sequence power is coming in, where power is being dissipated, how much it's being dissipated, and most importantly, specifically for thermals, we want to know for how long in order to determine what are the worst case temperatures. We also want to know what power is from the point of view of power supply design. Power supplies will be different between systems, and I'm going to get a little bit into that, what a system is on my next slide, but power supplies would be different, and we want to make sure we understand what the current draws are and how current draw would change with time, and specifically with different tests and with different functional modes. And lastly, for the typically for the end user applications, we want to where battery power is concerned, where battery life is concerned, we want to be able to model all possible states of the system, and especially cases where the lowest power state would become dominant, mostly because it's being at that state for a very long periods of time. Starting off with this, we want to understand what a system is. And in order to be able to do proper system modeling, we consider system to be everything that's between the model's power supply pins and the system's uh, power supply pins. Everything between that we consider to be system, and we want to plug in our power model into that. What's included in that is boards. It's included packages, or there may be other chip components as well. And on the right side, it's a good illustration of what different systems may be. There may be a part that goes into all these different systems, and most definitely there will be parts will go into two systems: end user and test system. So we want to make sure from the very beginning we treat all systems equally. For us, we don't make any difference between end user system and test system in terms of difference in models. Our models are the same, just we are able to handle the modeling of the different system. Scenario, we define it as a full set of parameters. That includes not only what the actual function is, whether it's executing a certain piece of code, but also it includes what are the voltage supplies, what are the temperatures, all the complete set of parameters which would affect power and thermals. So looking at these two definitions, would enable us to start planning for test as early as possible. And definitely we want to start planning for that at the architecture level. That is important because we want to be able to collaborate with chip designers. They need to understand what is happening in our test system, and we want to have a method of providing that information to them, that, hey, this is our test system. On the reverse side, we want the chip designers to be able to provide us their early data for us to work with, to be able to design what the test systems looks like, and make sure that we are within the parameters. And this is important to start this process very early on, because at that point we are already setting up the baseline constraints for electrical and for thermal. Once these are set, it becomes very difficult to change later on. This is a very, as you can see, this is a very wide area, what system looks like, what the considerations are. In order to be able to do that, we need to provide power, and the power models that come in with that need to be very, very flexible. We need to be able to update them through time with more accurate data as it comes in, and they need to be descriptive enough for end users to be able to use them. And one thing that parameters need to allow is they need to consider the fact that balance would be different for different applications. For what is going to be an end user application, the bounds for that are going to be different than what is going to be for test system application. Voltages, temperatures are going to be different. Process point might be different, right? The end user application might be a tighter process than what the test system would be doing. Temperatures would certainly be different. So that a model by itself needs to be able to handle that and produce power at these extended ranges. Our system power model actually has been designed with that in mind. It's designed with any system in mind. For us, anything is a system. Anything, we want to be able to handle it, and we want to be able to describe it. We want to be able to update it through time, and most importantly, we want to be able to mix and match different models, different technologies, still combine into one complete system. We are also we recognize that in certain cases some learnings from previous technologies would need to be carried over. So for that, we have a method to map technology which would allow early power review of chips to be entered into the system. This is much higher. Our model has much higher a level of abstraction than what Liberty has, which is the classical chip level model. Liberty cannot model many of the complex IPs. We can. We can model the regulators. We can model SerDes. We can model transaction power. And most importantly, we want to be able to scale up. The integration of dies on the same package, that's happening. That's been happening for a while, but we want to be able to connect together very, very complex systems, even multiple packages with multiple dies in them. For us, it's all the same. Doesn't matter. The key piece of all of this is actually 2416 power contributor support. We announced that support last year at DAC, and power contributors is what enable us to go outside of the typical bounds, to expand the power model boundaries. You can check out the tutorial we did on UPM last year at this link. I have, next slide, I'm going to speak exactly how we do that. In the classical model, a circuit is treated as a black box. We put it in a certain state, we measure the currents with specific process model, we capture those currents, and that becomes the model for us. The drawback for this is that the model itself is a fixed for a process model and for a purity point. It does not allow us to scale to different points. 2416 does this differently. It only captures specifics about what the circuit is. It captures a proxy model, and the actual binding to what the process model is, which process model we are going to use, and what process voltage, the temperature point we are going to specify, comes at the very end, at the point where we are trying to estimate power. At that point, we bind the two together and produce power. This enables us to virtually, with a single model, to estimate power at any process voltage and temperature point we have in mind, without limitations. That is where the power of 2416 comes, and that is where the application to extend the boundaries of the model happens. At CDX, we work at a flow at System Power, where what we try to do is take a system that was described earlier in a datasheet format. We convert those to a system power model, and also we get, for that system, we get ECXML format, and see if we can first of all use that description to drive the tools to estimate power for us, merge it with the physical format of the physical description geometries of what the system are, and merge both together and produce a final thermal analysis. Right, in the tools we wanted to demonstrate what the different scenarios are, how that work at the high level, what the different scenarios are, show the voltage modulation, and feed that into thermal simulation tools. There are multiple entities that helped in that. CDX was working on the overall flow. SI2 has contributed significantly from a UPM point of view, and also from demonstrating the viability of 2416. And most importantly, JEDEC released towards the end of last year the ECXML format as a standard. That enables us to now carry geometries of what the system is into thermal simulation tools. We implement that flow, but we are able to scale it. We can take any number of ECXML files. We can take any number of scenarios, and produce concurrently views for all these, basically for the full matrix of cases that people want to see. We can do that, and this is done at the high level of abstraction.
David, quick question. This is done at the high level. When would this need to be done in terms of time, in terms of product development, in your opinion?
So we would like to see that start early on, and develop initial views of what the system is as soon as possible. The reason being is once these views are available, they can be shared. The chip designers can see what the system looks like and plan for that. Right? The chip designers need to know where to place sensors, things like that. On the reverse side, system designers need to see what the power is. And starting early on, we develop these initial views, and then we progress through the flow by updating what the system is, what the power for the different chips comes in, and things like that.
Very early on, you mean before simulation, during device simulation, or during test development?
Before simulation.
Thank you. That's what I guessed.
Yep. All right. For this exercise at CDX, we used a design that was contributed by Ziglu. It's a 7-chiplet system. It's tiny, but it's perfect vehicle to demonstrate what the capabilities of this flow are. Right? We were not striving to model a full rack of chips and so on. Right? This would demonstrate the same capability as well. We developed the system model. We chose two cases, two scenarios to model to demonstrate that we can do both differently and in parallel. We looked at both power and energy because in this case it was power, but it was battery powered application. We wanted to see what the energy would be. I have links here in the slide for the full results. I'm not going to go into the full results here. I'm just going to show a couple of charts to give you an idea of the capabilities of what a system power model could do. As I mentioned at the beginning, system is could be anything, and in this case we had a package substrate with 7 chiplets on it. Each chiplet actually comes with its own tiny package. This snapshot demonstrates one that we can look at the hierarchy and see what the components are and define what each one is, what is the packages and so on. We can also look at from the electrical point of view. And if you pay attention, on the image on the right, we can put multiple chips into the same package, what the chiplet system would be. We can put multiple dies and package chips on the same substrate. All of that is perfectly doable. There's no constraint. Things could be mixed and matched. If we recognize the fact that the electrical connectivity of the supplies will change between systems, right? Whether how die supplies get bonded off to package pins would be different, maybe different between packages, and how packages get connected to on the board between different systems, that may also be different. That's fully configurable as well. That's the high level view of what the system configuration is. Now, next slide is talking about the scenario. What do we do here? And I have annotated different portions of this. On the CPU component that was inside the microcontroller, we are able to control that independently of everything else and specify its states. And you can see it went from sleeping to wake up. It woke up. It did some work. It did some compute work, which required higher frequency, right? Because it's actually DVFS system, so it goes up to high frequency, does processing, and this goes to those to wait for more work. If nothing happens, it ends up going back to sleep. At the same time, the radio would be it starts as off, and then it will turn on to send some data or to receive some data back, and then it will turn off while the CPU is computing. Those two happen independently. This is possible to specify very easy. We can see through time how this happens. And lastly, you're going to see that we use some voltage modulation as well to save power. And actually, one of the interesting aspects here is a person pointed out to me that, hey, how come at this point I'm not seeing a change in power? And the answer was, well, sometimes you don't save much power by changing the voltage, right? You cannot, right? The voltage is not that beneficial in all cases. So that was a unique insight that we gained from this, although it was the opposite of what we were expecting, right? We always expect to save power when we reduce voltage. But we were able to see what the power profile looks like. From that we can get the current waveform. We can get the charge as well, the energy consumption as well that's required. We can see the current changes and so on. So this is what a system power model in action looks like in time. Now, taking this a little bit to why we're here is to talk about thermals. And thermals are a very interesting topic. They depend on power a lot. And then thermals are done, thermal simulations would be done for different purposes, depending on which way you are looking at, at the system. If you look at it from a chip level point of view, what you want to understand is you can live with a slightly coarser view of what the system looks like, some simplified view. But what you're targeting is basically on that level, you want to understand where your hotspots are, where to place the temp sensor, make sure the temp sensor is placed where the hotspot is. Otherwise, you're not measuring anything. And make sure that, okay, I started, this early and I'm progressing through the flow. Is my temp sensor still placed where it should be? Do I have a problem? And I want to do that for the different systems, right? I want to do that for one functional operational system, another operational system, and test system as well. Test system is equal to all other systems. From from our point of view, they're all equal. We want to treat them the same. And on the other side are the system designers who want to understand how to design their systems with certain power view in mind, right? They want to see what the power is so that they can design their system and figure out what they need to add, what they need to move, how to place things. On the left side, the chip designers would be looking at die level at very low, actually very high resolution, at very small geometries, and figuring out what is happening. We also enable them to look at different metal layers, how they are, what the metal utilization is for different metal layers, and how that impacts the overall heat transfer. On the right side, we enable the system designers to go and explore what their system is. And I have an example here of this of the OmniChip that we use for this example. Is we can take a look at the outside, see what the temperature is, and we can take slices of the system and see what the heat, what the temperatures are in different points, and see what the heat transfer paths are, so that to enable us to enable the system designer to decide what to do next. Do they need to optimize, and how to optimize? And most importantly, we can do that view in a matrix of scenarios and physical systems by using different XMS files and ECXML files and different scenarios. All of that happens in parallel. It's an immediate view, and it enables people to decide which part they want to optimize and to focus on different aspects and to compare different systems. So in summary, system power model is unique, and it enables a high level power analysis and thermal analysis for any kind of system. We don't treat systems differently between test and functional. They're all the same. Most importantly, we recognize that this is a collaborative work between different organizations, between different people. We want to enable for data to be shared and for results to be shared, so that people can collaborate better, actually in real time. And as Dave had the question, we want to do that as early as possible, so we can see what are we dealing with. We want to enable that early modeling. And with that, I want to thank you and answer any questions.
Thank you, David. Appreciate it. There are actually a few questions. First ones have to do with how you interact with the rest of the system, if you will. For example, how do you enter the various thermal paths to model so that your model is accurate for the MCM and what have you, and the various paths that could be there? Let's start with that, maybe.
Well, so when the question about how are we, okay, I'm assuming this is the mechanical process, how we do that. Yes. There's different ways we can do that. One is obviously ECXML is one way to do it. We actually provide a full API. If anybody wants to go and play with that, they're more than welcome to actually do it. I think that's the ultimate flexibility. And then obviously we have a user interface where we have the different components where you can just drop them in and specify, okay, this is what I have here. I have a ball array that's like this configuration.
Okay. So in your hierarchical diagram, maybe it was just my understanding, but I didn't see any arrows between the die. I assume there's no problem with you modeling die to die, one die heating the other die.
That's not a problem at all. And this is actually inside this system that there are 7 chiplets. Actually, are you able to see my cursor pointing?
Yes.
Okay, so inside this package mold are the 7 chiplets, and in the cross section you can kind of see some of the die cross sections, and you can see the die to die heating.
Very good.
So yeah, that's absolutely accounted for. It has to be accounted for.
Yeah, I would assume so, but I just didn't catch it. And then the next level of onion to peel back, what about pattern elements? You mentioned early on that duty cycle is really important, and obviously duty cycle is controlled by the vector patterns. Do you have any links to help people understand that interaction?
So that's a very good question, and actually, sometimes what we recognize is that the exact duty cycle will not be known early on, but we still need to figure out what the system has to look like. And to do that, we want to try different duty cycles and see what happens. So duty cycle can be configured as parameter for the whole system. We can say, okay, it's 5 parameters which I have for 5 different duty cycles, and that becomes part of the simulation, for the simulation. I can see what the different options, what are the results, and that could become my constraining factor. I can say, okay, so this duty cycle, up until this duty cycle, it works. Beyond that, it doesn't work. Whoever is figuring out what the test should be, test sequence should be, needs to be aware of that.
And the final question I have entered is, as the ecosystem of an IC development, design, and implementation is growing in terms of data analysis. And is there a way to correlate your simulation results with actual ATE measurement results to help improve the accuracy of both and maybe focus our testing?
Yes. What we have, one part of the power model is it enables to actually capture, it allows for capturing a factual silicon measurement. So instead of me depending on early estimation or simulation or things like anything like that, I can actually take silicon data, plug it into my power model, and use that instead. Probably the best case for that would be if we have a service that's usually done much early on, or if I'm using a third-party chiplet that's already done, we have the data for that. We can just take it and put it into the power model.
So what you described is perhaps a circle where you start with a certain duty cycle and what have you, and then as the patterns become known, you can refine it. What about the other parameters like thermal resistance? I assume you start with an assumption there for chip-to-chip thermal resistance. Is that an analytical or a measurement, and how do you improve the accuracy?
So we would like to actually move slightly away from modeling systems as a single resistors, because that could be very, very misleading about what is happening in the system. We would like to start off with at least some kind of a drawing of what the actual system is. And from that, we can extract what the resistances are and work with that instead of assuming what they are. This is our first level of model that we use. And that model could be refined as often as necessary and see what the implications of that model change are.
And one more question that just came in. How do you deal with IP blocks? Do you actually get the data that you need? Do IP vendors need to provide models and parameters? Is there some challenge to getting the data you need? Let's put it that way.
There's always challenge to getting IP data, right? Just that's there, that will always be there. And the way we are hoping to do that is provide a tool that enables easy model generation. It could be plugged into someone's flow and extract data from there. It could be as simple as data entry. We want to enable that. And that's the key piece. How do we get the IP data? And that's our solution.
Okay, I think we're coming to the end of our time.
Would like to thank our sponsors, Advantest, Amcor, Indium Form Factor, and Nidec SVTCL. Advantest, a global leader in ATE, with advanced nanotechnology products supporting leading edge devices, with a global workforce in 50 countries and eco-friendly policies. Amcor, providing OSAT, advanced engineering and package leadership in their technology and quality, of course, in execution automation and starting with quality, and service, design and test through drop ship with a global manufacturing footprint, but local sales and support. And Indium, the premier assembly materials designer and manufacturer of thermal interface materials. We did talk a lot about TIMs today, but they have a wide range of them. Solder paste, fluxes, preforms, and metals and compounds. So I'd like to thank all the sponsors for making this event possible, and please thank them when you talk to them so that they know that they are appreciated. I wish everyone a good day and look forward to seeing everybody tomorrow. So thank you.